explain in English and see how it goes. So I'm going to discuss today the perspectives to implement a quantum internet in Recife. It's actually a mix of different projects that are beginning to combine with each other, and that's the movement I'm trying to explain to you today. So I will start with a brief discussion about what's a quantum internet, and then we go to discuss the laboratory of quantum networks that I implement there at UFPE, and then the different projects. So there is the project to build a quantum network in Recife, and then there is another project that's the Quanta UFPE, which is the implementation of an Institute of Quantum Technologies at UFPE. And then I'm going to discuss QWeb, which is a startup. That's a spin-off from my lab. And finally, some perspectives. Well, this is a broken figure to start with. So that's not the figure that should be there. So the figure that should be there is very simple. It's just a connection of sites. And so what we call quantum internet is actually just a combination of sites where you can process quantum information, and then these channels that connect these sites. So in a quantum internet, you should be able to do some quantum computing, but also quantum communication. And why would that be interesting? First of all, you could do the regular applications of quantum communication, like cryptography and quantum teleportation. And you can also do quantum communication at long distance or using multipartite entanglement, which opens different options to do quantum communications. And finally, you can do distributed quantum computation and also quantum sensing in the network. So that would be the broad interest to have such kind of system. So, one particularly important example which was, one of the inspiration to build the concept of quantum internet. So I highlight the last slide an article by Jeff Kimball's group, and he works in this protocol, and I worked in his group also in this protocol, in this project. And that's called the protocol DLCZ for long-distance quantum communications. And at the time, around 2005, so we were able to connect two distance atomic ensembles to do quantum entanglement between them. And we were also able to connect 4 different ensembles and to share entanglement in the polarization basis, so we could do cryptography. So that's how I was introducing the problem. And this was a general effort by the American government to develop quantum cryptography. The important point here is actually this was one of the first scaling up of this kind of quantum networks. And it was quite important to experience that, because once you scale up a network, you start to see that there are particular problems with that. Okay? And then I'll come back to this all over and over in the seminar. But there is a big problem, which is how to, when you scale up, you need to have copies of your system. And it gets really hard to do that with prototypes. If you start to put a collection of prototypes, then you get something that gets unstable really quickly. And so we learned many lessons during that time. And after that, actually, the group there at Caltech didn't continue with this research line. Nowadays, I understand why. Because actually, it's a very different way to do science if you want to build a quantum network, and not just to show the basic building blocks of it. And what happened is that in the end, the group there dispersed to different parts of the world where we built quantum networks laboratory. One in UFPE, another one in Paris, and the other one in Barcelona. And if we took that experience for different places. At Recife, in the meantime, since I got there in 2006, we actually worked in different problems. I worked with the DLCZ protocol there in Recife. we set up a photon pair source following together with a quantum memory, what's required for the protocol. And we started in a different lab, in a cold atoms lab, but then we built the quantum networks laboratory with this kind of source. But we also work with photon pairs from spontaneous parametric down conversion sources. And we are working in building a memory for this kind of source from crystals. But we also have a lot of works exploring new memories and new quantum states of light. So this is just to give an overview, because I'm not going to talk specifically what I'm doing in my lab, but we are taking this expertise now to develop a quantum internet there. So this is the team, the present team in 2025 in the lab. So it's a diverse group of people from myself, many postdocs and doctorate students and master degrees. And there is a very exciting time there in Recife, at least, with respect to the students. They are really, excited to enter in this new field, with many different things going on and new, I think, economic perspectives. And these are just the funding that's funding all the projects there. So let's go to the Recife Quantum Network. So the idea, our original idea is to build a small network. Okay, so we have inside the UFPE, we have two sites, one at the physics department and another at the electronic engineering department. And the channel here would be quite small, just half a kilometer. But we could also connect with a different university. It's a Federal Rural University of Pernambuco, and is about 6 kilometers away from UFPE. And so the idea of this project is actually to explore quantum communications at the telecom, okay? And for telecom, we have many different interesting things that we can do, okay? So we can build photon pairs that are broadband, ultra broadband, in terahertz bandwidth. And then we can combine that with dense wavelength division multiplexing, and this gives many different options. This is a current trend in quantum cryptography. Even though quantum cryptography is a node, a field, there are many different things going on, okay? And particularly, this trend of getting into the telecom regime and using these new technologies, then this comes with very interesting perspectives. So the idea is to build then quantum communication with entanglement, and of course to use this installed fiber, network of fibers. Okay, so what we have done so far, so we have already installed the fibers, so we set up this network, and we have already the source of photon pairs, the entangled photon pairs, and we already have photons traveling through these fibers. So what we are doing now is that we are finalizing the connection with this second university, just a couple of adapters in the end that we needed. And we are working the synchronization of the detections between different sites. Okay? And also we are working with the exchange of data, of package of data between the sites, so we can really start to have correlations from different sites. But we do have a problem, okay? So I think Red Hill and also in some cars they have the same problem. We just had around 1/3 of the resource that was really released for the project. And in Recife, at least, we try to do a lemonade with that, okay? So the idea is that since we have a small network, then actually we can work at 800 nanometers, where we have detectors, lasers, photon pairs, we have everything. And that was an adventure. It was not project to do that, okay? But it was an adventure of a small network. And just to give an idea of something that we can do, for example, we have our source of photon pairs. We can detect one in one site and then put in a fiber already in the network, because we can already just move the photons around. We install a network there in UFPE that will give us, a lot of freedom to do different tests. So we have 32 dedicated fibers between the sites, and we have 32 dedicated fibers also to the data center of the university, so we can actually move around a lot of photons. And then we can do different distance with that. There are some complications. We work with 800 nanometers because we have a lot of dispersion in the fibers. We are learning how to deal with that. But we can already see that our quantum correlation, so what I'm plotting here is just a cross correlation between the two photons as a function of the propagation distance. And when you have a number above 2 in this matrix, you have some quantum correlations. And then you see that I can get to 5 kilometers still with a lot of quantum correlations. So we will get to the rural university. I don't think there is going to be a problem with that. But we are still dealing with this, how to work with these broadband photons. So then we enter in another project, which is this thematic center from FINEP. It's the Quantum UFPE. So the idea actually is to combine some initiatives from different groups at UFPE. So we do have a quantum technology, quantum information group at UFPE. I mean, that's very active. I mean, we've been in the Institute for Quantum Information since its beginning. I mean, in 2002, I think. And so there is a research line that's well settled. And we have a theory on quantum information. We have main experimental works on quantum optics, and also with quantum memories. But we also have a strong collaboration now with the engineering department, especially electronic engineering. And they have a different set of expertise. I mean, they know how to work with cryptography, with optical networks, and also to do more electronics, especially electronic of systems. And actually, production engineering had another project for quantum computation, actually for applying quantum computation for optimization problems in engineering. And the Center of Informatics also had a quantum computation initiative that was born from their artificial intelligence group. And then they worked a lot of different models for quantum computation. And actually, these different groups were already, engaged in different projects. So we have some quantum internet projects with the physics department. We have this quantum network project between physics department and the electronic engineering. The production engineering department also had a project just for this, to do this optimization with quantum computation. And the Center of Informatics, together with physics, with the theoretical groups in physics, had another project also for optimizing NISC device. Okay, so we combine all these ideas to start to work together, okay, and then build a center for quantum technology there. And so we had the project approved, and we are now setting this institute in a floor of an old building, which used to be of Sudene, is a very old institution, but nowadays the floors are just empty, and then we are projecting to build we are starting to build the institute there. So what's going to be the first lab that we are planning there? What's the focus of the institute? So the focus is to build a photonic quantum computation lab, okay? So we are going to use the single photons from our atomic source together with photonic circuits and detectors, and then try to go to photonic quantum computing. And we are also going to have another site from our quantum network. So when we put this together, then we start to have some quantum network with capacity, with processing capacity. And also had this year a INCT, the National Institute of Science and Technology for Quantum Computation, Applied Quantum Computation, was also approved there. And so there is many projects that are combined together around this quanta. Okay, so actually so what's the idea of our quantum computer. And there, as I mentioned, there are 3 parts. Okay, so we have a magneto-optical trap that are providing photons, and we have a photonic circuit, and we have a bench of detectors. So the idea is that the photons will come from the quantum networks laboratory, from our traps. So we have already some versions that are more aligned by construction, and then we are working on the design to get a more plug-and-play trap. But the interesting thing about the protocol that we are used to generate single photons is that it is scalable in the sense that you can synchronize the single photon source. So our goal is to have at least seven memories synchronized, so we can get at least 7 photons simultaneously. And then we can couple them to fiber arrays, okay? And these fiber arrays would go to the photonic circuit. That was a very recent development. So these photonic circuits, these universal photonic circuits, which allows us to tweak the circuit as we use it, okay? They become commercially a very recent development. And we just found what we need very recently, actually this year, from this company, Ethos, from Milan. And so we are acquiring this photonic processor that can get up to 20 modes. This would be around 10 qubits would be equivalent, and would be calibrated and then completely reprogrammable. Okay? So this would work at the frequency that we like to work with atoms. This is 780 nanometers. That's for the rubidium atomic traps. And the last set is already more well established. That's a set of detectors of 32 SNSPD detectors with high efficiency, above 90%, and with low dark count, and also optimized for 780 nanometers. And so now we have all these elements that we can put together. And the idea is actually that we should have that work at least not full for the magneto-optical trap, but at least with 1 or 2 photons, at least for next year. Okay. And so what can we do with that? So that's actually as important as build the machine is what to do with that, because that machine is hard to maintain. I mean, you have to maintain that detector of the cryostat. You have to do each 2 years a large maintenance. But we are already starting to discuss how we can do, for example, chemical calculations with that kind of processor. This is just, on the top is just an example of a use of a smaller processor to do some calculations of energy levels in molecules. And below is another application of this kind of circuit for vibrational dynamics in molecules. There's also a lot of work with this, to do adaptive boson sampling, is another way to call this kind of problem, but to do machine learning with this kind of circuits as well. So for the collaboration on the left, is a collaboration with Cesar, which is a startup accelerator there in Recife for computer science, and the chemistry department is already a collaboration going on. And on the right, we have the collaboration with the informatics center. Actually, this kind of quantum processor was a demand from the informatics center. So what happens is that for computer science, I mean, they can work with the quantum computers online, but they're not very transparent about what's going on. And a large work is to optimize for the noise of the particular machines. And so they want to focus more in a particular machine that they can control everything, and then try to work with develop the environment for programming and things like this. So they want to have a machine to work from the bottom to top with the software. And so that's why we chose actually this application for the Institute, because many different departments want to have this kind of initiative. So that's, I already mentioned, the perspective is to have this installed up to next year. And we are actually rushing with the development of applications. I mean, as soon as we install it, we have to start using it. So for quantum computation, this is a small quantum processor, but it's a way that we can connect with different initiatives worldwide that has a larger scale. So companies that follow through this kind of hardware, there are some. I think the most well-known is PC Quantum and Candela. PC Quantum in United States and England, and then Candela in France. But there's also this Turing Q in China. All these companies, they work with this kind of photonic quantum computation. And then, actually, our process there in Recife that we're learning how to use this kind of computers, we can actually connect with these other initiatives. But, of course, this is not the only goal with that processor, because this also allows us to do applications in quantum communications which are much more advanced. And the thing is that even though it's a small processor for quantum computation, it's actually a processor of a good size to explore, the frontier for quantum communications, okay? Because for that kind of problem, so you enter with the advantage of security. What you gain is maximum distance and efficiency of the process. So what we're looking at is this kind of protocols to build quantum repeaters, especially this one. I think it's more well adapted for the hardware that we have now is a protocol that only requires single photons, and there is no memory. So to start with, this would be a good start. But you see that the cluster states that you need to build, they're not as large as you usually need to build large applications in quantum computation. So we can really explore this kind of protocols well, I think, already with that kind of processor. And finally, as I mentioned, we have the problem that once you start to build a network, you need copies, okay? And then you need to have your hardware to have really a grade like a commercial grade. You cannot, there is really no quantum network without a market for this network. I think this is a message that everybody should think about, because it is a large project. You really need to build many copies, and it is spread, and then you need to occupy many locations and different teams. So to deal with that problem, we have a spin-off from my lab. I founded together with Alexandre Almeida and Marcelo Souza this company, which is, the focus is really to provide the basic hardware for this kind of system. And the idea is to form a partnership with the laboratory. So the laboratory enters with the equipment and components and materials, and the company develops the prototypes until it gets really to be robust, as would be necessary for commercial applications. We have a project recently approved in this call from CNPq, this call for researchers in companies. That was quite important, so we were able to hire people, engineers, projectists, and our first products would be really to focus on the photon per source and on the atomic traps. Why? Because that's what we need to do, everything that you want to do in the network, okay? So if you don't have these parts to be robust enough, it's really hard to grow. So what's the perspectives? So this is just an imaging of the city with our networks just schematically drawn on it. Look, the bold red lines, okay, they are already set up. These are the links that are already established. And the dashed red line, you can see this is the link that we are going to build with the institute, with the Quantum Technology Institute. And so now we are going to put this quantum computer there, and this is a very particular quantum computer because it works at 780 nanometers, and our network, we are starting to build at 800 nanometers as well. So actually, this is actually the lemonade. It was not we found a way to work with the network. It's because since our network is small and we start to work at 708 nanometers, then we have all these elements together now. So we can really think about a small quantum internet at Recife. because we're going to really have some processing capability that we can connect with the network. And this is, of course, is later in the future, maybe 2027, 2028, to start to play with the processor together with the network. And of course, if we receive the money, okay, if we receive the rest of the money from the project, then we can go to telecom. And that would be quite interesting. So what we gain telecom with respect to 800 nanometers is mainly the distance in the fibers. You can reach more places. But actually, you gain more technology, because the technology at telecom, you have many devices that you don't have at 800 nanometers. But on the first impact will be the distance. And so if you look at Recife, we have already two other institutions, UFPE, the University of Pernambuco, and CESAR, which is that accelerated startup accelerator institution there in Recife. And actually, all the institutions that are presently in the network, and these two institutions, they are all in the same RNP network. This is not also a large network. The overall circumference here is around 33 kilometers. So if you have the detectors telecom, you should be able to connect all of these institutions in Recife. So with that, I'd like to thank you for your attention.
Questions?
Thanks, Daniel, for the great talk. So actually, it's kind of two questions. One is, one of the difficulties of working with these programmable circuits is that entangling the photons is very hard. And I'd like to ask you to comment a bit if your MOT sources they can produce, and I mean, if you can like create a cluster state out of your 7 sources. And also regarding going to telecom range, aren't you giving up the fact that you have quantum memories? And I mean, how can you address that working at telecom?
Yeah. So, first of all, we can generate cluster states from our memories, but we are not planning to do that on the short term. We are planning to do the simplest use of the memory, which is just to synchronize them. And then we are going to use the memory just to get the various memory synchronized. So we are planning to enter in that processor with just single photons, independent single photons. Of course, to do the quantum communication protocols, we are going to need to start with work with the quantum entanglement. But that's part of the problem. And actually, it's been quite interesting to start to work with the engineers, because many of the problems that the physicists, worry more about, for the engineers, they're not that bad. So, for example, to do phase stabilization of large networks, that's commonplace for people at telecom, for the, I call the coherent communications. And the other question for the telecom, for the memory, yes, to work with the telecom in the beginning, we are not going to have the memory. So our quantum internet is going to still be that small one, at least for a while.
We have a question from a student. I'll pass to you later.
Thank you for your talk. I was wondering, how do you measure the quality of the entanglement according to the distance? You showed that.
Yes, actually, what I showed there was a number correlation, which is kind of entanglement, but it's just easy to test. And the way I measure is really just, I measure click here, and then I have a click on the other side, but I have to compare with the level of independent coincidence. I mean, I have the probability to have one photon, the probability to have another photon. If I multiply these two, I have the probability of accidental coincidence. So that G12 is a normalized correlation function, is what we measured for coincidence divided by the accidental coincidence. So if I have up to 2, that's a standard kind of process, you can have like thermal source that would give you that. Above that, that's more indication of a quantum process.
See. Thank you.
Felinto, you mentioned that you're going to be working at 800 nanometers, but at those wavelengths, right, the fiber is multimode, correct?
Yes.
Yeah, and do you see that the dispersion that you're talking about was modal dispersion or was chromatic dispersion?
No, that's chromatic dispersion,
Chromatic
mainly.
dispersion, because you probably will have a lot of modal dispersion too.
Yes, probably. But for the protocols that we are going to explore, that won't be a
That
problem
won't
in
be
the
a
beginning.
problem because you're
No.
only detecting amplitude, so you don't care so much.
Yes, and actually, to do many different things with that small network will be actually simpler. For example, if we do BBA4 for cryptography, we can use just a pulsed laser, and that's really narrow band, and then we're not going to have chromatic dispersion. Actually, in the beginning of quantum cryptography, they spent maybe 1 decade doing the experiments at 800 nanometers.
Even on fiber?
Yes, yes.
Yeah.
So it is not new, I would say.
Okay, okay. All right.
Thank you very much, Felinto. Back to the mode conversion, because the fiber that the infrastructure is for telecom.
It's for telecom.
It's telecom. So you're planning to, as you said, to go to the telecom afterwards. But for this distance, it's not a problem using 800, as you said. But for longer, like as you plan to have other points of your network in Recife, could you continue to use 800 or
No.
this is no because of the distance?
Of the losses.
Yeah,
I mean,
okay.
the graph that I showed is a monologue graph. So it's linear on the x-axis, but on the vertical axis is really logarithm. So we wouldn't be able to go another 2 kilometers above. Maybe, I mean, we could get to 10, but it would be really like 30 dB losses, things like this.
Thanks, Daniel. Well, being a neighbor, I'm particularly excited about all these initiatives. So, like initially, you plan to have 3 nodes in the network, right? So I have 2 questions. Like one is, you plan to share tripartite entanglement or bipartite entanglement between the nodes? And one thing that it's particularly important for quantum networks is the ability to make measurements on an entangled basis. Can you do that in your system, or how difficult would be that?
Oh, I can do. I mean, you mean the photonic circuit to do the measurement, the entanglement base? I can do it. I mean, with that photonic circuit that we're buying, I can certainly do that. But I think if we can do just one measurement, you can do a circuit that's simpler, just in one side. But the idea is to do a tripartite entanglement, of course.
Tripartite.
Yes, this is not in the project, but it's in the fact that I have 3 different nodes. That's the whole idea. And so we are setting up, we are planning actually to do a completely symmetric triangular network in which each site would be a generator of photon pairs and also have a detector capability. So we could really do something symmetric.
Okay.
But we're still figuring out the need to the synchronization of the generation of the photons. So the simplest source are CW photon pair sources, but these are harder to synchronize. So we are thinking about how to do if we're going just to pulse it or to go to femtoseconds. This is the thing that we are considering.
Thanks.
Hi, Daniel. Thanks for the talk. Just a quick question. You had some works with memories with vapor cells, right? In hot vapor cells. So would it be able to do this quantum computation with those memories, or what would be the advantage to work with the cold atoms in terms of simplicity, right?
No, they are a requirement actually, because for that protocol that I generate photon pairs with the atoms, it's a probabilistic protocol in the same way as a parametric down conversion process. But since I have a memory, then I can actually keep the photon, and actually the memory allows me to synchronize different photon sources.
But you have memory with the vapor cells, don't you have?
With vapor, I mean with the magneto-optical trap.
No, with the vapor cells, hot atoms.
If I'm going to use the memory of the vapor cell, no, I'm not planning for now. It's just because it's a more wild system for the memory. I still didn't learn how to control that.
Just a quick question. How indistinguishable are the photons from the magneto-optical traps? Because I imagine they are very, very indistinguishable compared to solid-state sources.
Yes, actually, this is an advantage of this system. I can make them very, very indistinguishable.
So let's say over 99% or something?
Actually, not really, because what happens is that these photons are generated closer to resonance, okay? And this means that I can control the purity. It's different than a spontaneous parametric down conversion source that you are working already for very low probability. Then you already have a very low two-photon component. This one I can tune. So actually, I have to see the task that I want, and then I can tune the purity to get that. So it can get as pure as a photon pair source. But usually, we work on the limit. So if it's 99.8%, if you really need that. If I can work with 95% or 98%, I can tune the source to be that.
Okay, but in terms of indistinguishability, what's your major limitation? Is it the temperature of your trap, or?
No, the major limitation is efficiency, because if you want more purity, you need more memory. So you can synchronize the sources. And so that's the trade-off. The purer the state, the longer the memory. And then basically you have to start to work in the memory all the time and then start to improve it.
Okay, so it's like saying that if the better your cavity, the narrower the line, but then your cavity has a huge lifetime and the brightness goes down, something like that.
Yeah, but you have to work for that. But it's workable. That's the good news. But it's hard also. So what's really limited the indistinguishability is the two-photon component. That's what we found.
Okay.
So that's how we got, I mentioned that I start with that scaling up with 2 ensembles and 4 ensembles. So that was critical to having distinguishability. That's why that was a problem that was not solved, but understood at the time.
Okay, nice, thanks.
Thanks, Daniel, for your nice talk. So playing quantum communication needs components, and components are very expensive. I'm interested in the photonic device you showed from EFOS. Can you tell me what's the fabrication technique? I mean, it's a 3-5 device, a glass device.
So they burn, they do waveguides in glass, okay? And then they put some resistors on top of the waveguides. And so what they can do is they can have universal beam splitter. Is equivalent as you'll be able to switch the splitting ratio and also tweak the phase between the 2 outputs. They can do this sequentially. I think the most impressive thing about this device, this is not the only company. There's another company, I think in Netherlands, that does that. But that company was more amenable to work with scientists and build for the specific wavelength that we wanted. But I think what's more impressive is the fact that they can calibrate that circuit. So they can calibrate in a way that what we are going to give is a transfer matrix. And you can give the identity, and then what you get in the input, it gets out in the output. But you can do, in principle, anything there. But we need to learn really how the device works. We are probably going to be one of the first customers of this company. I mean, you ask for the manual, they don't have, they send something to us. But I think it's a very interesting device. It combines quite well with what we had in mind. So that's why we are really willing to work on that with the company.
More questions? I think we should.
We are going to continue the conversation.
Yeah.
Okay, so seems that we can go on for the coffee for the moment, and we'll get back, say, 15 minutes will be fine, so we don't put much delay. And then we can get, remember that there will be a roundtable session at the end with all the speakers, and then there's another place for discussion beside the coffee. So see you in 15 minutes. Coffee is being served up here. So see you in a few.